So in the last segment, we ended with a Maxwell solution and got a value. I'm reducing it down to just 3 significant digits here. And what I did now is I put it into a spreadsheet where I'm comparing the two numbers for the electric field at 100 millimeters away from the point charge. And I've got a value of 9.42 times 10 to the 11 volts per meter from Maxwell. Our original solution was 8.99 times 10 to the 11 volts per meter. In this simple calculation, I'm just looking at basically the analytical result, subtracting out the Maxwell result, dividing them by the analytical result, and you can see I'm taking the absolute value and I'm multiplying by 100. So there's different ways to compare numbers, whether it's test data compared to a theoretical data or different theoretical values, things like that. And I'm just doing a kind of a quick estimate here of what the percentage of the difference is between the two numbers using that formula. So 4.8% is not too bad, but it's really instructive to see how the computational process works, how the numerical computational process works, to be able to improve that result. So what I'd like to do now is move into another simulation where we make a small refinement, and then we'll see if that compares a little bit better and it gives us lots of topics to discuss. This is the model that we ended on, Project 4, the default Maxwell design. By the way, it's worth noting within this report, if I double click on the number itself, I can change that number format to something other than decimal. So if I go to scientific and I'll apply it, that's a little bit easier to compare the numbers like we were doing in the spreadsheet. So what I want to do now, and hopefully you can follow along with this, I've got a saved result, and I'm going to right click Setup 1 and copy it. And if I click on the top level node that says Analysis, I'm able to right click and paste it. So all I did was copy and paste Setup 1. You can see it automatically changes the name to Setup 2. And the reason I'm doing this is because I want to change one of the settings in the setup here that has to do with the accuracy of the solution, where we're determining what the percent error is. I'm not going to give a detailed discussion about how that works. I just want you to see the impact of the change here. And I'm going to go ahead and I'm going to change it to 0.01. That's a significant change, and you'll see the impact of that. Depending on the hardware that you're using, if you've got a computer that maybe doesn't have a lot of RAM, or you've got fewer processors, you might change it instead of 0.01 coming down an order of magnitude. Maybe you make it something like 0.05 or something like that. You can play around with those numbers, but if you feel comfortable, you can give this a shot and see what happens. So actually, let me go to simulation. I'll do a quick validation, and of course nothing would be expected to change there. Let me just go through the analysis. I'll right click Setup 2, and I'm going to analyze. So I'm not getting rid of the old result, but I've got a new setup that's taking place. So it's got different settings to try when it runs that calculation. So watch this flip through these different adaptive passes. We're already up to 7. I want to show you what's happening here. If I go to results, and if I go to solution data, I'll get another window. I'm up on a different screen. So when I bring that over here, I can see this thing called convergence. And here's a table of data where every added row is giving us new information about the solution for what's called an adaptive pass. And I haven't really described that yet, but I will probably later on. The key is this delta energy figure. So that's the error in basically the computation that's taking place. And when I change it to 0.01, if I go, instead of the table view, if I go to the plot view, and I will change, I'll change this to delta energy as well. What's happening is that every successive pass, it's doing something different to the computation. And if it compares the result and the accuracy is not within my criteria of 0.01, then it's going to make a change and it's going to resolve it. And it's going to do another comparison. And it keeps doing that until we hit this threshold of 0.01. And in a later segment, we'll talk about exactly what's happening, but it has to do with this number of what's called elements, changing the mesh to be able to improve the accuracy of the solution. So for now, my only job really is to wait until this thing converges, and I see this red line. You can see sometimes it actually goes backwards. In this case, it looks like it's on the right track, and it's encouraging that maybe within another minute or so, we'll be able to get down into a converged solution of 0.01. If I go back to the table view here, it's hard to know how far you're coming along with your computer setup, but if the solution is taking an incredibly long time, there's good reason why you just might not make it with the hardware that you have. I happen to be solving, I'll show you how to get the setting later, but I happen to be solving using 16 cores on a technical laptop computer. So I have pretty good faith that we're going to get there pretty soon. One thing that's happening is that, notice this number of tetrahedra. So when we started out, we were looking at less than 3,000 total tetrahedra. So those are the elements, and I'll give a better view of what that looks like soon. But notice with every subsequent pass, the number of elements are increasing significantly. We're down here, for me, I'm still not converged yet, but I'm at 313,000, almost 314,000 elements. And you can see the percentage of energy, of delta energy, is actually improving along the way. But it's coming at the price of these additional elements. And you're seeing the impact in the solution speed of your solve right now. It was much different with the original setup 1 because we had a much looser criteria. And if we go back and look at that result, in fact, I should be able to do that here. I can go to setup 1 and I can see, sure enough, I got my delta energy criteria, which was below, we just set it to 0.1 instead of 0.01, and we got there with less than 30,000 elements. So we're paying a big price in the solution time, and also the RAM. If I right click and look at my task manager, I can see here the RAM requirement that I have is I'm already almost at 21 gigabytes of RAM. Your machine might simply not have that much RAM, and you could have possibly timed out with an error by now. If that's the case, that's okay. You can basically run a solution with a lower convergence criteria, like I had mentioned before, 0.05 instead of 0.01. You can play around with numbers until you get it right. So if you are having an issue getting that solution, let me just go ahead and close this. You should see information down here. If it looks like you've got a progress bar that keeps moving, I'm still on adaptive pass 21. You might see something here in your message manager that tells you otherwise. What I'm looking for is full convergence, and I'll get that notification that shows up underneath my Maxwell 3D Design 1. And I got a feeling it's probably going to happen any second now, but if yours times out, you would actually see an error message or something indicating that it has not converged. It doesn't mean that it's a wrong solution. It just means that it did not achieve the accuracy that you were looking for. So I think that's something good to be aware of as you move through this.